Okay, we're recording.
Okay, so thanks everyone for joining. Today's speaker is Dana Taupanu, and she received her PhD in mathematics from KU Leuven in June 2022. And during her thesis project, she studied the factors contributing to the initiation and propagation of stealth coronal mass ejections by means of numerical simulations, but also from spacecraft observations. She analyzed the influence of previous eruptions during sympathetic events and the contribution of the background solar wind on the resulting geoeffectiveness. And in parallel, ever since her master's thesis, she has been fascinated by coronal fans and would like to study them more in terms of how they fit in the complete picture of the solar corona. And she is currently working on a variety of topics as an instrument scientist at the Royal Observatory of Belgium, including detector testing and calibration, data analysis, and spacecraft observation operations. And today she will discuss a numerical and observational study of stealth and consecutive coronal mass ejections. So Dana, please go ahead.
Thank you so much for the introduction. So, as I said, I will present basically my PhD work, and I will start with an introduction on CMEs, CME sources and signatures, stealth CMEs, ICs, and their space weather effects, the simulation setup that I used to analyze these, my results, and the force analysis on these simulations. And I'll conclude with some remarks. As probably all of you know, CMEs are some of the most energetic solar phenomena, and they expel plasma and magnetic field. And you can see here an example. I will use my pointer. Okay. And a sequence of CMEs you can see in the LASCO coronagraph images. As there's another one. And most of the times they are associated with other solar features such as solar flares, filaments or prominences, dimmings, and post-eruptive arcades. And these are called source signatures. Because they point to the origin of or they're correlated with the origin of the CME. And here you can see an example of, in the top left video, an example of a filament erupting. And what's one of the most well-known filament eruptions. And in the aftermath, you can see the post-eruptive arcades. Now, stealth CMEs are a particular type of CMEs that you can see them in the coronagraph images, but they lack the low coronal signatures that I mentioned that they're usually associated with. And they're usually narrow, slow, and some occur in the aftermath of other eruptions. And in this video, I'm showing the first stealth CME investigated by Eva Robrecht in 2009. And you can see clearly the CME erupting, which was associated with a streamer cusp, and no low coronal signatures can be seen on the disk or close to the disk. After the eruption, they propagate in interplanetary space, and they're called RCmes. And when they arrive at Earth, they are associated with some particular characteristics, such as enhanced magnetic field, smooth rotation of BZ, an increased dynamic pressure in the front, low plasma beta values, and also a decrease in the DST index, which I will explain a little bit later. And if they arrive at Earth with a negative BZ component, they are of particular interest because they can magnetically reconnect with Earth's magnetic field. And this allows energetic particles to enter the magnetosphere and then can create some not so positive effects. And they can induce pipeline corrosion, or they can irradiate the crew and passenger on board airplanes. They can also increase the atmospheric drag and lead to deorbiting of satellites and many other effects that are really important in our current technologically based society. So the approach problems that I analyzed in this work, I wanted to understand how shear emotions, which they are a widely accepted mechanism for CME triggering, how do they affect the subsequent eruptions, and how do stealth CMEs form, how do the background magnetic field influences the eruptions, and how other CMEs affect the propagation and the geoeffectiveness of such eruptions, and how do they differ as opposed to single eruptions. And the final part was the force analysis of the propagation and evolution of these CMEs. And for more detailed analysis, if you wish to have a look, you can look at these papers. Okay, so I started the analysis with the 2.5D MHD version of the code MPI MRVAC. And I initially simulated a triple arcade structure embedded into a bimodal solar wind. And to obtain CMEs, I applied the shear motions that I previously mentioned, and they are time-dependent shear motions, and I applied them onto the lowermost polarity inversion line, the southernmost, and this increases the magnetic pressure gradient inside the arcade and actually leads to CME creation. And in order to analyze the effect of the background solar wind onto the subsequent eruptions, I also increased the temperature of the background solar wind in order to increase the speed at 1 AU. And it had the effect of increasing it by 50 kilometers per second, but actually also had the effect of splitting the initial triple arcade structure into a northern streamer and a southern pseudo-streamer. This is an overview of the scenarios that I obtained. Well, just a brief of the most interesting simulations, and because I took a lot of intermediate ones, mostly a parameter study. And with the difference between these is the shearing motion and the amplitude of the shearing speed imposed, and the triggering mechanism of the second flux drop, because always the first flux drop that erupts, it's caused by the imposed shear motions, and the second one can differ as a function of the amplitude. So with the highest one, in the slow wind case, I obtained 2 flux drops caused by the boundary conditions. A little bit lower, the second flux drop actually failed to erupt and was created by the reconfiguration of the coronal magnetic field. And even lower, which was an interesting reversal, the same flux drop that failed to erupt, in this case actually erupted, but in the same manner, what formed from the reconfiguration of the coronal magnetic field. And with the lowest one, I obtained a single eruption and a single flux drop as for comparison. And what was interesting is that in all the cases in the slow wind, I obtained many trailing plasma blobs. And this was not the case for the faster wind. And I tried to analyze if there was any stealth in this second scenario, the second background scenario. And I imposed the same shear motions. And actually, the resultant was similar to the double eruption in the slow wind case. So both flux drops occurred while the time I was applying the shear motions. And again, another case with a single CME for comparison. In the bottom panels, you can see an evolution of the arcade inflating, creating the flux drop, and evolving and being deflected into the equatorial current sheet and erupting. And I'll start with the analysis of the first 3 slow wind scenarios. And I'll show you first the 2 CMEs that occurred from the shear motions. And you can see here the first flux drop, which is very similar for all slow wind cases. And the second one that has a similar path, is quite large, and it's also deflected towards the equator. The second case was with the first flux drop also erupting from the shear motions and getting deflected northward and into the equatorial current sheet. And in this current sheet, in the aftermath of the first one, there was another flux drop occurring and reconnecting with the northern arcade. And by lowering this shearing speed, counterintuitively, the flux drop that failed to erupt now actually gets also deflected into the equatorial current sheet and erupts. You can see it here forming, being deflected northward and erupting. And this is what we call the stealth CME, because it occurs after I stop the shear motions, and the reconnection occurs higher than 1.4 solar radii, and given the previous studies, this would show that there are no low coronal signatures associated. In order to see that my simulations are actually physical, I also compared them with a case study with two CMEs that occurred in 2009. One that was associated with a prominence eruption, this one, and the second one, you can see it here erupting, was actually not associated with any low coronal signatures, and that is why we considered it a stealth. So it would fit in the eruption and stealth scenario, and that is why I wanted to compare it with this case, but also with for an interesting analysis to see how it compares with the double eruption, where the second one was also triggered by the impulse shear emotions, and actually fit better with this case, where the second CME was triggered by the shear emotions. And to analyze this better, not just by size, good, because size-wise, the second CME in the double eruption fits better, because the stealth is too narrow and too slow. I took the high time plots of the front of all the eruptions, and I plotted in black the two CMEs from the observations, and this is the first one, and this is the second one, and in blue is the first CME of both scenarios, and because the shear emotions don't differ that much in amplitude, they were basically overlapping, so I only plotted one line. And the pluses or crosses represent the front of the second CME in the double eruption case. So even though it's a little bit delayed, the speed, so the speed fits better the second CME observed, and this would indicate rather than as opposed to the stealth speed, which was much slower, and this would indicate that the stealth CME that we called the stealth in the observations would actually lack signatures because of our capabilities, because of our instrumental capabilities. I also propagated these two scenarios to Mercury and to Earth, and nicely enough, the observed CME was actually erupting on the same line as was on the Sun, Mercury, Earth line. So I could actually track it in 2 points. And at Mercury, so the messenger was orbiting around Mercury, and I could also compare with the data from it. And the arrival time fits almost perfectly. Also, the amplitude is pretty good. The nice reversal of BZ also matches, and the dip in the BY component and the B total also matches the dip in the observed total magnetic field, and this could also indicate to the double eruption case. But it is the drawback is that my flux drop are a little bit shorter. I'm trying to understand why. And by the time the CMEs arrive at Earth, the signatures become distorted because it is a weak ICME seen by wind and ACE, so in L1. So the correlation is less good, but it is still a qualitative fit with the in situ measured values. You can still see the increase in the dynamic pressure in the front, the increase in the BY, the nice evolution, reversal of BZ, and also the smooth decrease of the speed, which shows the expansion of the CME. Now, the faster wind scenarios, which were the two flux drops occurring from the shear motions, even though I applied the same speed and the same amplitude as the one that triggered the stealth in the slow wind and the single eruption. The first one, the stealth speed, is shown here, and it's actually much faster, surprisingly, because I applied the same shearing speed, and I did not change the magnetic configuration. And this is a single eruption, which is simple, boring, just one flux drop erupting and getting deflected towards the equator. Here I'm showing an overview of the 5 simulations that I showed, and here the top and middle row show snapshots of the simulations at 13 and 22 hours respectively, and the bottom row shows snapshots when the flux drops are at 1 AU. And you can see the slowest one is a single eruption and a slow wind. The fastest one is the stealth speed and the faster wind. And I also see here the two flux drops that occur. Here is a stealth. This is the second CME in the double eruption. And actually, in 22 hours, and this is time from the start of the shearing motions, the two CMEs actually merge and magnetically reconnect. And they also arrived at 1U as one entity, as opposed to the scenarios in the slow wind case, where you can still see the magnetic structure of the following plasma blobs. Okay. I also investigated the geoeffectiveness of these simulations by computing the DST, which is the hourly average of the deviation of the horizontal component of magnetic fields measured at ground level. And I computed the DST from my simulations using a modified version of the model of O'Brien and Ferran, which is dependent on the speed, BZ component, and the dynamic pressure in front of Earth. And if you're interested in this model, I have a backup site that I can show you how I calculated. And I compared with the observed values for the event that I analyzed. And also here, it fits better with the double eruption case, amplitude-wise. And which is a bit striking because usually in literature, multiple CMEs are regarded as more geoeffective, and they interact and they have a larger influence on the geomagnetosphere. But here, actually, in this case, the smaller one, stealth, doesn't, the eruption have more geoeffective impact than the double eruption. And I analyzed the different contributions of the BZ component and the dynamic pressure onto the DST. And it starts with a storm sudden commencement, which is given by the increase in the dynamic pressure. Then it decreases along, the DST decreases along with the dynamic pressure. It tries to go back to its original state, and the BZ turns negative. So that's when it starts decreasing again and follows the trend of the BZ, because the model disregards the positive values of BZ. And the minimum of DST is approximately 2 hours after the minimum of BZ, which is actually the time difference between L1 and the measurements at the ground level. And once the BZ starts to go back to positive values, the storm, which is not really a storm because it's only, in this case, minus 15 nanotesla, but the storm-like evolution enters the recovery phase. And in the recovery phase, you can actually see still the contribution of the dynamic pressure onto the DST. So the resultant DST is an interplay between the BZ and the dynamic pressure, not of just the BZ. And here, it's actually really nice to see it's a two-step geomagnetic storm resultant only from one magnetic flux drop, because this is the stealth speed case where the two flux drops merge and they arrive as one at 1 AU. Then I calculated the geoeffectiveness of all the simulations that I presented. And the case I showed before was actually the least geoeffective. And the most was the eruption and stealth. And I attributed this to the fact that all the CMEs arrive at Earth or 1 AU with a positive frontal BZ. And the negative trail reconnects with all the trailing current sheet or flux drops and decreases the negative flux, and therefore also the influence that it has on Earth. And this to test this theory or this reasoning, I reversed the sign of BZ and I calculated again the DST. So as if the CMEs would have erupted from a reversed arcade. And actually, the geoeffectiveness was increased for all the simulations, and it was more grouped as a function of the background solar wind, which was expected because The only difference that would affect the front would be the background solar wind and the very small changes in the shearing motions. And this can actually be seen in the lines. And these plots were overlapped to the minima for an easier evaluation. And here, the three cases also are being grouped as a function of the slow solar wind, and the double eruption case becomes the most effective. So my conclusion from this was that multiple CMEs can actually be less effective if given the recognition of arrival at Earth and the orientation of the magnetic field. And the final part that I analyzed was with the forces, using the forces in the MHD momentum equation. In the left-hand side, I have the total force, which is given by the plasma pressure gradient, which is almost always radially outwards and decreases with r to the second. Plus the magnetic pressure gradient, which tends to expand the arcades and the flux ropes. The magnetic tension, which tends to confine because it's oriented towards the center of the flux rope, and the gravity. And using these components, I wanted to understand why the first CME erupts faster in the faster solar wind case, even though I applied the same shear motions. How does the stealth CME form? How do the plasma blobs form? And to analyze the propagation and interaction of CMEs. And the first bullet was to understand why the first CME was faster. I took snapshots when the front of the arcade, of the inflating arcade, and of the future CME was at 2 solar radii in both cases. So the left-hand side is the single eruption in the slow wind, and the right-hand side is also the single eruption, but in the faster wind case. And you can see on the left-hand side that as the arcade inflates and it gets deflected towards the equator, it also magnetically reconnects with the northern arcade. And this creates overlying field lines and increases the downward confining magnetic tension. And this actually decelerates the eruption. Whereas in the faster wind case, because of the change in the magnetic topology, the northern arcade is smaller and it doesn't interact as much or not as early not with the erupting arcade, and the two arcades, they remain separate for a longer time and allows the arcade to erupt faster. To understand the stealth CME formation, I plotted two snapshots before and after the formation. And on the left-hand side, you can see the first CME erupting, and this is indicated by the green arrows. And there was also a second flux loop that formed from the shearing motions, but that actually fell back to the sun because it didn't have enough magnetic pressure accumulated in the flux loop to make it erupt. And this causes the current sheet to expand, and the magnetic pressure gradient from the sides pinches the current sheet and thus creates the plasma blob, or the plasma blob-like stealth CME. And this also follows a similar path to the first CME, and that is why it erupts. And it erupted as opposed to the failed one, even though it had a less shearing speed, because it was less deflected. So it had less accumulated magnetic pressure gradient. It had less energy. It was less deflected towards the north. So this actually allowed it to nicely be ejected into the same current sheet. The other blobs that form in the aftermath of all the eruptions, and these are formed actually in the equatorial current sheet in a similar fashion, but they're caused by a different process, because the northern arcade gets really shrinks because of the compression of the southern arcade as it gets deflected towards the equator. And you can see it here in the yellow field lines. This is the first CME, And this is the arcade as it is after the eruption. And as it tries, because I did not change in the meantime the magnetic configuration, this tries to relax to its original state. And it does so by elongated the streamer cusp. And also here, I didn't show it, but I calculated it. It's a similar fashion that the magnetic pressure gradient pushes from the sides and creates the flux ropes that keep being ejected in the aftermath of eruptions. And this happens even a day after the eruption itself. And the X points represent the X points between the formed flux rope and the top of the new arcade, the northern arcade. And the time evolution is towards the right. So here you can actually see that it is increasing back to its original state. Okay. To analyze the propagation interaction of CMEs, I chose the most interesting case, which was the double eruption in the slow wind, and I tracked it throughout its propagation. And I took slices along the equator, and I'm plotting here. I'm showing only the logarithm of my detention because it easily tracks the flux ropes. And you can see, so the first flux rope, you can see it here, and how the second one merges and forms a plateau. And here, by the arrival of the two CMEs at 1AU, they are merged. You can see still the following plasma blobs. This is the end of the tail, and this peak is the reconnecting equatorial current sheet in the back of the CMEs, and this is already the back solar wind. And for a more detailed analysis, I took a snapshot of this, several, but I'm showing one, where you can see the front of the first the front of the first and the front of the second flux ropes, the ends of the first and the second, the end of the tail, the plasma blobs, and this is the front background solar wind. And what is interesting, this is the nice plateau inside the first flux rope. And the most interesting feature is this peak in the plasma pressure gradient. And this gives the only contribution in the black line. This gives the only contribution to the total force, which is in green. And this evolves in time and increases in time. And I wanted to see if this was a shock. And I did so by taking slices at different times of the eruptions. And you can see here where the front was at 35 solar radii, it's basically no peak formed yet. And this is at 1U, and they're both in both background solar wind cases. They're both formed, and the faster one is a little bit more ahead than in the slowing case. And to see if there are shocks, I calculated the characteristic MHD speeds of the background solar winds. I plotted them in the fast magnetoacoustic speed is in red and dotted red, and the slow magnetoacoustic is in black line. And these star speeds represent the speed of these peaks with respect to the background solar wind. And they are higher than the speed of the characteristic MHD speeds of the solar wind, and which makes them a shock. So even slow CMEs can actually create shocks if given the right properties of the propagating background solar wind. And that was very quick. These are my conclusions. And when I started this work, it was I obtained one of the first numerically simulated slow CMEs. Within 1% difference in amplitude of shearing speed, we obtained 3 different eruption scenarios, completely different, which were the 3 that I showed in the slow wind in the beginning. The same shearing speed applied in different coronal configurations result in different eruptions. And this could indicate that the photospheric conditions that we see in for instance, the radial magnetic field is not enough to predict CMEs and to predict their initiation. And we do need some coronal properties from density or temperature. The occurrence of small blobs is dependent on the initial magnetic configuration, so it could also be an indication of this, an indicator of the origin. We obtained a two-step geometric storm. I put it in brackets, in quotation marks, because it wasn't really a storm. A storm would be when it's less than some say -30 or -50 nanotesla, but mine was -15, so it wasn't really a storm, but it was a storm-like evolution, which was created by only one flux drop. So the DST, the resultant geoeffectiveness, is an interplay between the BZ, but also the dynamic pressure. So also the conditions of the background solar wind contribute a lot. And the multiple CMEs can even have a reduced geoeffectiveness as compared to single CMEs. And usually the studies are backwards. So they take we take the most important solar storms, and then we go back to the sun. And of course, if it has a reduced geoeffectiveness, then it would imply that there was basically no storm, even though there were 2 or 3 CMEs one after the other. And we don't really do that. We don't really go. So we need the other way around. We need solar parameters and to make models to predict the CMEs from there and their geoeffectiveness. This point was regarding the northern arcade that can disrupt because of the magnetic reconfiguration that created the overlying field lines, can disrupt the nearby eruptions and either confine or decelerate the eruption. And the peak in the plasma pressure gradient can evolve into a fast shock by the arrival at 20U or even further. And this technique of vector decomposition has been applied, or I applied this to 2.5D MHD simulations so extensively for the first time. I hope, I think, if I've read enough the literature. And it proves to be a valuable method of solar eruptions analysis. And thank you very much. I would love to hear your questions.
All right, thank you. Does anyone have any questions? Ritesh?
Hi, Dana.
Hi.
I have actually a couple of questions.
Sure, great.
So, in your simulation, do you also consider the rotation of the CMEs as they pass through the heliosphere?
No. And I can't really do that because it's 2.5D.
Yeah, that's what I was wondering because
Yeah,
that
I
may
know.
also change the in situ
I know.
measurements.
Yeah. And that is one of the limitations. Of course, during the, so that's I was going to say that assuming the orientation of the arcade is the same as the orientation of the CME is held as the initial orientation of the arcade. This
Mhm.
is one of the major ifs of this model. And
Yeah,
yes,
but
of course, it can rotate.
yeah, indeed, it's a great work. Like we have been following this, and if you remember, one of my colleagues had been working and has been in touch with you for this. Uh,
Yeah.
yeah, and the question that I wanted to know, like you mentioned that these slow CMEs also give rise to shock, but what I like believe till now is like when a CME is slow, it gets just carried away with the solar wind. So what's your take on that? So like how does it create a shock? It's still not so clear to me.
Well, it was, let's say, a little bit faster. It was like 50, it was slow, but it was still faster than the background solar wind. It wasn't just dragged by the wind. It
Oh,
was, yeah, I do have the plot of the speed here. So this was supposed to simulate. This line is the background solar wind, the speed of the background solar. So it was 340, and this was supposed to simulate this part. And the difference, let's say it's 380. So let's say 40 kilometers per second higher.
okay, okay. Yeah, nice.
So you can still see the difference,
Yeah, there's a difference. Okay, great.
even though it's very, very, even though it's very low.
Yeah, I
which
may not have
would be
noticed it.
exactly the same, and it would be just carried away. It will not create any shock, but it's
Mhm.
still slow. You wouldn't consider a less than 400 kilometers a second CME a fast one, right?
Yeah, yeah, true. Yeah, thank you.
Okay,
That's
thank you.
all.
Thank you.
Yuhong has a question.
Yeah, thank you for the nice simulations. It's really
Thank you.
impressive.
Thank you.
I have a question about you call them stealth CMEs. So do they produce post flare loops, right? You have reconnections and then they
You?
don't.
No.
Sorry,
They don't create post loops.
the reconnection doesn't. You don't. I mean, you have current sheet very high up. That's why.
Yes. Yeah.
Okay.
Yeah.
And
It's
then
higher than.
so
Sorry.
you have a. So it's the heating. The they don't produce the post flare loop signatures on the.
No, because
Okay.
it's basically reconnection in the after current sheet. So there's no. I can show the. What can I show? No, this one. The force analysis at the end. This one. Okay. So this current sheet has basically these are the loops at the bottom, and the reconnection has nothing to do with these loops, and it's just reconnection inside the current sheet itself. It's just the pinched current sheet, and it doesn't. Also, it's higher than 1.4, and it was a study of I think Eva Robrecht. Yeah, that she analyzed several cell CMEs and the depletion of the coronal material, and also saw that above 1.4 the process is too high to actually leave any signatures either on the in the very low corona. Yes.
Okay.
And also it was after the stop of the shear motions, and that was also a clue that it doesn't have any post flare loops or any signatures, and
No
it's
flare
actually,
ribbons either.
yes, no ribbons. No,
Okay.
for sure not. No.
Count. Okay. Thank you.
Thank you. Will gladly answer any more questions or suggestions. I love those, and feedback.
Any final questions? If not, then thank you again, Dana, for a nice presentation.
Thank you so much for inviting. I will try to stop sharing.